Hi, my name is Patrick Vaughn, and today I'll be discussing my results from Lab 3, which consisted of finding the mass of a black hole. In this lab, I created a computational model of a star orbiting a black hole. The star's trajectory was calculated using my email address as a seed. Using the star's motion data, I calculated the gravitational net force acting on the star, and from there I used the net force, the star's position, and mass to calculate the mass of the black hole, which I found to be 7.3152 times 10 to the 34th kilograms. Here are some initialization conditions for my model. I assigned the star as the system and the black hole as the surroundings, where the only force acting on the star is the gravitational force of the black hole. My time step is 86,400 seconds, and the mass of the star is 2 times 10 to the 30th kilograms. The fundamental principles I used were the momentum principle, Newton's second law of motion, and Newton's law of universal gravitation. Here's the equation for rate of change of momentum, which is equal to the summation of its parallel and perpendicular components. This equation also represents the total net force based on Newton's second law. Next, I have the formulas for the parallel and perpendicular components of the net force. The parallel component of the net force points parallel and in the same direction as the object's motion. The perpendicular component points perpendicular to the object's motion towards the center of the Kissing circle. I use Newton's law of universal gravitation to find the mass of the black hole. This principle describes the forces of gravity acting on a pair of objects, which is dependent on the object's masses and inversely proportional to the distance between them. To calculate the mass of the black hole, I will set the force of gravity equal to the net force from the computational model and solve for the black hole's mass. Here's what my computational model looks like. The black sphere is the black hole at the origin and the yellow sphere is the star. I'd first like to note that the yellow arrow represents the magnitude and direction of the net force, while the black and red arrows represent parallel net force and perpendicular net force respectively. As you can see, the forces grow exponentially as the star approaches the black hole and shrink back down when the star gets further away. This is reasonable based on Newton's law of universal gravitation. As the distance between them decreases, the force will increase by a power of 2. Here you can see the initialization conditions of my code. At the bottom is my calculations for the components of the star's velocity, based on the position vector that was created using my email address as the seed. This part of my code is the most crucial. Here, I go through the steps to calculate the net force and its components from the position and velocity of the star's motion. I set initial and final momentum equal to the mass times the initial and final velocities. I then found the change in velocity and the change in momentum. Next, I implemented the momentum principle and found the rate of change in momentum. Based on Newton's second law, I set Fnet equal to the rate of change in momentum. Here I calculated the parallel component of the rate of change in momentum by multiplying the magnitude of the rate of change in momentum by the initial momentum unit vector. I then set this equal to the parallel component of the force, and used subtraction to find the perpendicular components. Once I found Fnet for all data points in my model, it was time to calculate the mass of the black hole. Again, I used Newton's law of universal gravitation, but I solved it for the mass of the black hole. I used 6.674 times 10 to the negative 11th Newton meters squared over kilograms squared for the gravitational constant. Through this process, I found the mass of the black hole to be 7.3152 times 10 to the 34th kilograms, or 36,576 times the mass of the Sun. Typically, black holes range from 1 to tens of millions of solar masses, so I feel that this value is within the range of acceptable results. So here are some follow-up questions. What does it mean? How is net force different from the rate of change in momentum and its components? Well, essentially, net force is what causes the change in momentum. Numerically, they are the same. However, the net force causes an acceleration, which is a change in velocity, and therefore causes a change in momentum. So, net force is equal to the rate of change in momentum, but they are not the same thing. What if the black hole was swapped out for a different black hole at the origin? If the star's motion remains the same, it would be impossible to find a different value for the mass of the new black hole. In this lab, the star's motion is predetermined and not based on the gravitational net force of the black hole. Basically, the star's motion decides the mass of the black hole, and if that does not change, then neither will the black hole's mass. That's all for now. Thanks for watching.